All right, finally in the inner solar system, I want to look at the Earth-Moon system. Oftentimes we think of the Earth and the Moon as being a single system because of their similarities in size, and also because, as you may remember from before, we believe that they formed from a single collision. And so just a reminder of how we think that happened. We had the proto-Earth, and this proto-Earth formed possibly as a second generation planet from even larger planets that were called super-Earths, which were driven together and collided due to the close approach of Jupiter to the inner solar system. And then the debris that was left behind created the proto-Earth, a smaller planet, along with Mercury, Venus, and Mars. But this proto-Earth is probably about the same size as the Earth of today, but with more water. And then a Mars-sized object comes in, not Mars itself, but a Mars-sized object, and collides obliquely, meaning that the center-to-center collision, that would be a head-on collision, but oblique means that it hits from the side. And that oblique collision then threw a huge amount of debris out and melted both objects and created a disc-like structure that surrounded the proto-Earth. And so at this point then, the disc-like structure, and you can, I'm going through this kind of quickly because this is a review of when we looked at this in the formation of the solar system. But this material in the disk was actually part of the planet at this point, and was rotating fairly rapidly and mixed very well with the material that was at least in the outer mantle of the proto-Earth. And then the disk then cools and forms our moon. Actually, according to the best theories that we have, formed two moons. And then those moons collided to eventually form our moon. Okay, and so the result of all of this then is the Earth-Moon system. Now the moon is about 1/4 the radius of the Earth. It has, because it's 1/4 the radius of the Earth, that means that it's 1/64 of the volume. But because the moon is made mostly of mantle material, the small core, so mostly it's this rocky material with, at most, a little small metallic core. The moon is lighter in density than the Earth. The grams per cubic centimeter is less. And so this means that the mass of the moon is only 1/81st the mass of the Earth. And so what I'd like to do first, before I look specifically at the surface features of the moon and the surface features of the Earth and the interior structures of both, is to look at the effects of the Earth on the moon that come from tides. Now, a tidal force, if we take a look at the effects of the Earth on the moon, are forces in which the gravity acts unequally on the near side of the object versus the far side. And so with unequal gravity forces, this produces a stretching effect. This is called tidal stretching. Why is there unequal force of the Earth on the near side of the moon versus the far side? Well, because of the inverse square law of gravity. And so there's a strong distance dependence of the force of gravity of the Earth on the moon, and so it's going to pull harder because on the near side, because the near side is closer to the Earth than the far side is. And when we have a difference in force, even though both of the force vectors are pointing in the same direction, the fact that there's a difference in force is equivalent to a stretching. You know, if I had, say, somebody pulling on this arm at 200 pounds of force, and then in the same direction pulling on this arm with 100 pounds of force, then even though I'm being pulled in the same direction by both forces, because the forces aren't equal, it's equivalent to me being stretched apart by 100 pounds of force. And so that's essentially what's going on here. And that's why we have this elongation of the moon in the direction that points toward the center of the Earth. And so that elongated or elliptical shape then is held in place. And so the effect of all of this then is to keep the moon's same face pointed toward the Earth. So if we have the Earth here, and then the moon is like, and I'm exaggerating the elongation here so that we can see it more clearly. It's just a little tiny bit of elongation, but the moon actually tries to break free from that, and there's a slight rocking motion back and forth like this. And so if you watch for long enough, you can actually see 5/8 of the surface of the moon. But for our purposes here, we can think of it as pretty much being locked into place so that the same face of the moon, this face here, if there were, say, a crater here, that crater would still be there, that crater would still be here, and then that same crater would still be there as it goes around and around the Earth. The Earth essentially locks it into place. And so this is a tidal effect then, and is very significant effect of the Earth's pull on the moon. And so this is oftentimes why we refer to the other side of the moon as the dark side of the moon, even though it's not any darker than the side that we see. The quote, dark side of the moon is illuminated equally to the side that we see, but it's just from our point of view here on the Earth, we can't see it, so we don't know what's going on with it. Unless we take pictures of it, and I can show you some pictures in a minute of what that other side, that back side of the moon looks like. And it's kind of interesting too. But here, we might wonder, is this the only object in the solar system that experiences that kind of an effect? And the answer is no. When we get to Jupiter and Saturn, we'll see that 4 of Jupiter's moons always keep their same face pointed toward Jupiter because of the same kind of a tidal elongation. And with Saturn, the moon Titan keeps its same face pointed toward Saturn for the same reason. Okay, and so there's a very significant effect then of the gravitational tidal forces of the Earth on the moon. So if we look up for a moment at the data projector, here we see kind of an interesting picture. This is one in which the Earth and the moon are in the same phase. You can guess which direction the sun must be in this picture. It must be way over to the right. And this is a picture taken by the Galileo space probe on its way to Jupiter. That what it had to do first was go to Venus, and it actually stole a little bit of Venus's orbital energy away, and that essentially doubled the speed of the spacecraft, so that it can make it to Jupiter faster by taking this roundabout trip to Venus first, and then doubling its speed. And so on its way back then, it took this picture of the Earth-Moon system. Here is a picture of the formation of the moon. Now this is kind of a more traditional picture that doesn't show the synestia that I had mentioned earlier, which was that disc-like structure that we think is responsible for the composition of the moon being almost identical to the composition of the Earth. Is that it formed first into this disk, which is another state of matter for the planets when they are molten and spinning rapidly. So this is a more classical view of how the Earth-Moon system formed. But unfortunately, this can't explain the perfect match to the composition of the Earth and the Moon. And so this is why that synestia idea is taking hold. And so here's a picture then of the moon. But this, of course, is the side of the moon that we can see. It's got dark features called maria. We'll talk about more in a second. So these kind of the things that make the face on the moon. And then we have the lighter, more heavily cratered regions called the lunar highlands. And then here's a closer up view of that. Beautiful picture. And so I wanted to talk just for a second about these tidal effects. So the Earth has its effect on the moon, creating that elongation. But the moon also has its effect on the Earth. So the moon pulls back on the Earth. Newton's third law tells us for every force, there's an equal and opposite reaction force. And so the effect then of the moon on the Earth is also significant, although not as significant as the effect of the Earth on the moon. Okay, so here's the Earth, much bigger object, moon, much smaller object. But the moon still pulls harder on the near side of the Earth than it does on the far side of the Earth. And so instead of elongating the whole planet, it creates these little tidal bulges. So these tidal bulges then are associated with the difference in force between the moon pulling harder on the inside part of the Earth than the far side of the Earth. And so these then are regions of high tide. Okay, and so we can imagine this then better perhaps with a globe. And so the moon then is pulling, let's say, from this direction and creating a bulge here, but then also, and this is sometimes hard for people to understand, is how do you get a bulge in the opposite direction? If the force is this way, let's say the moon is out here, if the force is this way and then less strong this way, then how does that create a bulge? Well, remember what I said before about a difference in force creating a stretching effect. And so it's like the Earth is being pulled apart because there's that difference in force between the inside part and the outside part. And so that creates a smaller tidal bulge on the far side, but a larger tidal bulge on the near side. So let's take a look at this for a second and imagine that that tidal bulge is here. Okay, so here would be the moon pulling on the Earth. I think you can see then that that would tend to pull water up toward that tidal bulge, and so this would be high tide here. On the other hand, though, if the tidal bulge were down here, then that would tend to pull water away from the coast, and so that would create a low tide. Okay, and so these regions here are regions of high tide, but then halfway in between them, and let's say this is the Earth's North Pole there, so that we're looking down on the Earth's North Pole, so this is the Earth-Moon plane that we're looking at here, then these would be regions of low tide. And then also on this other side, that would be a region of low tide as well, because the water is more deformable than the land. The land might only deform a few centimeters, but the water can deform by as much as many feet, even tens of feet, depending on the conditions. And so if water is being pulled away from here, then that's going to pull water off the shorelines. And if the water is being pulled toward this area, that's going to create higher shorelines in the areas that are associated with the higher tidal bulges. Okay? And so these tidal effects were much more significant in the past because the moon was much closer to the Earth in the past. The moon is moving away from the Earth at about 3 centimeters per year. A little more than an inch per year. How do we know this? Well, we put reflectors on the moon and we bounce laser light off of those reflectors, which is not an easy thing to do because the laser light has a tendency to spread out on its way to the moon a little bit. And then that light, as it comes back, has to be picked up by a receiving array here on the Earth. But it sounds easier than it is. It's actually a very difficult thing to do, but we've been able to get quite an accurate assessment of the exact distance between the Earth and the moon, and we can measure that to accurate to millimeters per year. And so if we extrapolate backward in time, what we find is that the moon was something like 15 times closer to the Earth than it is today when it first formed. So maybe instead of 240,000 miles, might have only been 20,000 miles or so. The moon appeared huge in the sky. The moon would have looked about like a dinner plate held out at arm's length. And the tides in those days, because the moon would be so much closer, you'd have a much bigger difference in force. And so the tides in those times, when the moon first formed, were huge. By huge, I mean that we could have had 1,000-foot breakers all the time. And so this was not a time when the Earth was as habitable as it is today. Very violent events were taking place. We had huge amounts of tidal variation, and the tidal zones were being ravaged by intense, very turbulent waves. Okay? Now, if we extrapolate, though, to the present day, eventually the moon got smaller and smaller, from our point of view, of course. It's still the same size, but it got smaller relative to its apparent size because of its increasing distance away from the Earth. And so finally now, today, the moon can just cover up the sun, and so a total solar eclipse is possible. But it's an amazing coincidence. That would not have been true. Say 1 billion years ago, the moon would have been bigger than the sun, so it would have easily covered up the sun, but now can just barely cover it up on the average. But in the future, the moon will move farther away. And it won't be able to cover up the sun, so solar eclipses will be impossible. Total solar eclipses, I should say. And it's thought that in about 1 billion years, the tidal forces of Jupiter acting on the Earth will be stronger than the tidal forces of the moon acting on the Earth. And so the stability that we talked about earlier, in which the moon is able to hold the Earth's axis in place, will not always be that way. And it's estimated perhaps in 1 billion years, the moon's tidal forces will have dropped to the point to where we will no longer have that climate stability. Remember, the Earth's orbital axis is held in place because of the torques that are produced by the effects of the gravity of the moon acting on the Earth. And so as the moon moves farther away, eventually the Earth's axis will start getting more chaotic, and then finally we'll end up with the kind of climate catastrophes that we believe have happened to other planets like Mars.